In this next lecture, we will look at the concept of cache and memory. We are going to try to look at how do we map things from a large memory to a small cache, and the one way we are going to look at first is a direct mapped cache. So from our previous discussion on memory hierarchy, we have seen that cache needs to be much smaller than our main memory or the hard disk. So if I can draw a quick diagram, that's my cache, very small, and I have a pretty large memory in comparison. We need to answer two questions first when we talk about cache. So when the processor looks at the first is going to be in the cache. So when you try to access a word, how are we going to know whether that particular item or word is in the cache? And if we know that it is still in the cache, how do we find it? So these are two related questions which we are going to try to answer in this lecture. So we need some sort of a mapping technique. I hope you guys see the problem. We have a very small cache and we have a very large memory. So if we need to bring things from the memory to the cache, we cannot bring the entire memory into the cache because of the size difference. So we would need to bring things one at a time. So what we are going to do is we are going to establish a many-to-one mapping from the memory into the cache. Let me just write this. This is my memory and this is my cache. So the problem is which addresses in the memory are going to be mapped to what addresses in the cache. So the only way to do that in a simplest design is to establish a many-to-one mapping in which each item in the lower level, there is going to be one particular location in the cache where it might be. So the idea is to have sections of memory mapped to the cache. So that gets our many-to-one mapping from the memory to cache. So that's called a direct mapped cache. Here is an example of how a 5-bit direct mapped cache would look like. Now we have the two levels. The upper level over here is the cache, in which we have 8 words. The capacity is 8 words. And in this example we have a memory which is much larger than the cache. In this case we have a 5-bit cache, so 5-bit memory addresses are being used. So that corresponds to 2 raised to 5, which is 32 words in the memory. So 32 words in the memory, and there are 8 words that can possibly occupy the cache. And a quick note here, 8 words in the cache consequently means that we would need 3 bits to index the cache. So each word would need 3 bits to identify in the cache, and there are 5 bits in each memory address. So the memory addresses are going, say, from 0 all the way to 31, so that's 32 words, and in the cache you have 0 to 7 at each time. So the memory capacity is 32 words. We need 5 bits to address each memory location, and only 8 words can occupy the cache. So how are we going to map them? So at a time we can only have 8 words, so we can say memory address from 0 to 7 can occupy the cache, or it can be the next 8, or it can be the next 8, and so on. Right, so we are going to get 4 different possibilities here, 4 groups of 8 words that can at any given time occupy the cache. Over here, there's the last 3 bits over here, 00001 for example, 101 for example. Those are directly going to be the same as the 3 bits that are used for the cache index, and the first 2 bits are essentially going to identify which block is in the cache. So my prefix, which I'm going to later call as the tag index or simply tag, is going to be the first 2 bits. So you have 0001, 10, and 11. Let me highlight those here. I have prefix. So my prefixes are that, and the last one would be that. Alright. So how do I find the cache index, say for a given memory address? Almost all the direct mapped caches are going to use this particular formula to find a word. We are going to be talking about blocks in just a bit, where blocks are essentially groups of or collection of words where one word is 32 bits. So you could have this formula changed to a block memory address and number of blocks in cache. For now we are just focusing on one word per block, so we are going to be talking about word address and number of words. So suppose we wanted to find the cache index of something in memory. The address is denoted as X right now. To find the cache index, we would need to do a modulo with the number of words in the cache. In our example, the number of words in the cache were 8, so that goes over there, and X is a memory address. So we can take a look at any one of the 32 addresses. Right now we are focusing on this one. So we have 10001, which corresponds to 17 in decimal, and this is 8 in decimal. So if you divide 17 divided by 8, the remainder would come out to be a 1 and that's going to be the cache index for that particular memory address. And if you look back over here, that essentially means that this location 10001 would map to that. In this case, it just happens to be the same last 3 bits. And it is going to be exactly the last 3 bits of the memory address. 3 bits because of the capacity of the cache. So if it's 4 bits, if it's a 16 word cache, then it would be the last 4 bits. In this case, we have an 8 word cache, so that would be the last 3 bits. So if the memory locations are a power of 2, in that case we can just pick up the last 3 bits. In general though, we can use this method to find the cache index. Now here is the continuation of that example. On the top we have the 8 word cache. Each different word in the cache is indexed by a 3-bit sequence. We have a 32 word memory at the bottom. That's my lower level. And the lower 3 bits of the memory address are over here specifying the cache location or the cache index. So let's see, what is the 5-bit memory address range? The 5-bit memory address range in this case is 0 to 31, and for the cache it's a 3-bit cache address range. It's going to be from 0 to 7. So in total we have 2 raised to 5 locations here, words here, and in cache we have 2 raised to 3. So that means 2 raised to 5 divided by 2 raised to 3, if I divided those up, I would get 4 addresses that are going to be mapped to one slot, cache slot. So those 4, I'm going to highlight them. So I've got 1, 2, 3, 4, 5, 6, 7, 8. That's 1. That's 2, 3, and we can use the same yellow for last one. So there are going to be 4 in this particular example. For each memory address, as you can see for the blue one and the red one over here, there's a unique slot in the cache. There's a unique cache index. Many of the memory addresses are mapping to the single cache slot, in this case 4. So there are 4 blue ones mapping to the same cache slot over here, there, and the last one. And then there are 4 red ones in the memory that are going to map to the single red cache slot. Now that is going to be true for each set of addresses that are going to be separated by 8 words, as I have shown in different colors. Now let's talk about the memory address, the word address, and the cache index and how they relate to each other. So we've already seen that the memory address needs to be 5 bits because it's a 5-bit cache. And we have seen that the cache index needs to be 3 bits because it is an 8-word cache. So to find the word address in memory, we are going to need 5 bits. Those 5 bits are a combination of 3 bits from the index, and there are going to be 2 bits called the tag bits or tag index. Those are going to identify which particular group of 4 is currently being mapped in the cache. So the tag bits are 2 bits. So those can be highlighted as 0, 0 or 1 or 2 or 3. So those 4 are going to identify which particular block is right now being mapped in the cache. So if you combine the 2 bits of the cache, well, those are going to be the most significant bits, and add the 3 least significant bits from the cache index, that's going to give us the word address in memory of 5 bits. So tags are really the ones that are distinguishing which particular block is right now being mapped in the cache. Alright, so let's talk about a realistic size of a cache. Here we have a 32-bit direct mapped cache. So out of that 32-bit address, right now we are using a byte address, which means that we should be able to access all the 4 different bytes inside the word, and our byte offset is going to help us do that. So we need to establish a 32-bit address. That 32-bit address is going to be a combination of some tag bits, some number of bits for cache index, and then we are going to have 2 bits that we need to suggest the byte offset. We need 2 bits because 2 bits in the byte offset because there are going to be 4 bytes in each word. So if the byte offset is 00, that means that is the first byte of a particular word, second byte of a particular word, third byte of the particular word, and the 4th byte of that word. Now let's talk about cache index. The cache index right now, it says it is 10 bits. So where is that 10 bits coming from? That is coming from essentially the size of the cache. The size of this table over here is showing you the cache entries. And because we have 10 bits right now for a cache index, that means we have 2 raised to 10 or 1024 locations in the cache. At each location you have 1 bit for valid, so you have a valid bit. You have a few bits for the tag, in this case 20 bits. And then you have 32-bit data that is present at that particular cache location. So when we try to access, when we are trying to read something from memory, we are going to try to look at it in the cache. Now, how do we know whether it's a hit or not? Whether we have found it in the cache or not? Well, for this to be a hit, first of all, two things are going to need to happen. This is an AND gate. So the first thing that needs to happen is the valid bit over here needs to be a 1. Valid bit is 1 means that there is a valid data entry at that particular location. Otherwise, it is going to be 0. So we need some sort of valid data present at that location for the valid bit to be a 1. And also, the output of this comparator also needs to be a 1, which means that we are going to try to see if the 20 bits that are in this tag field are the same as the 20 most significant bits of the memory address we are trying to access. If they are the same, that means that the memory, the group of memory locations in the cache are mapping correctly. Otherwise, we will need to change that. So if this is 1 and this is 1, that means we have a hit. And the data can be read through that 32-bit sequence right here. Let's see. So if you have a 32-bit address, we have taken up 10 bits for cache index because we have 1024 location, and we have taken up 2 bits for the byte offset, which means that we will have 20 bits for the tag. That's how we are able to find out how many bits are in the tag field. Let's answer a few questions here. First, how many words are there per block? Well, if you look at this particular column, these are data that is present at, so these are words. So word 0, word 1, all the way down to word 1, 0, 2, 3. And there is only one such column. There are no multiple columns here, here, and so on. Which means that in this case, I have 1 word per block. If you had more columns, that would mean that you have more words per block. Block is essentially a horizontal orientation, and words are going this way. Words are going vertically down. Now let's calculate the cache size. For cache size, we need the number of words. So in this case, we have 2 raised to 10 words. And each word is 4 bytes. So that would correspond to a 4 kilobyte cache. That's how we are going to know whether things are present in the cache or not, and how we can quickly find them. Now, the next question that we are going to try to answer is, how about having more than 1 word per block? Clearly, if you have more blocks, then you can probably access a wider memory, more locations in the memory by having a wider cache. So let's take a look at that over here. The block size in this example is 16 words per block. So we have, let's say this is block 1 or block 0, block 1, block 2, and so on. right? And at each block, if you can see, right now we have 16 words that are present at each block, and so on. So what would be the block offset? Now the 32-bit byte address has the tag bits as before, cache index as before, but it also has a block offset field so that we can select one from the 16 words, because eventually we will need a 32-bit word. So we are essentially widening up the memory cache table over here so that we can fit more things into the cache. The byte offset functions the same way. So 2 bits that are going to be used to access each byte in the in a word, the same way as before. So let's suppose that we have a cache size of 16 kilobytes in this particular example. So I'm going to say cache size here, and I'm going to assume that it is 16 kilobytes. Then how do I find out the number of blocks? Well, number of blocks in that cache is going to be given by, take the total cache size and then divide it by the number of words per block. In this case we have 16 words per block, and then each word is 4 bytes, so 4 bytes per word. So if we do that, we are going to be getting the number of blocks, which in this case should work out to be 2 raised to 8, which is about 256 blocks. So this is going to be 2 raised to 10 plus 4, 14. This is 2 raised to 4. This is 2 raised to 2. And then you can subtract the exponents and find that out. So 256 blocks. So 256 blocks in this cache also means that we would need 8 bits to specify which block. So block 0, block 1, block 2. So the last one should be block 255. So that directly gives me how many bits I need in my cache index. So cache index, that implies that my cache index should be 8 bits. Which is what I'm using over here. I would need 4 bits in my block offset. That's essentially because of 16 words per block. I would need 4 bits to select from 16 options. This is 2 bits as usual. So now if you wanted to find how many bits should go in the tag field, that should simply be tag should equal 32 in total minus 8 from the cache, 4 for block, and 2 for byte offset. It should give you 18 bits. So that's how we get to the number of bits in the tag. Alright, so how is this selection process working? Over here we still have the valid bit. We are still going to get a hit in the cache if the valid bit is 1. And also the tag field that is common to all the words in that particular block is the same as the memory address that we are trying to access in the tag field here, 18 bits. If they do match, then the data from each of those words is going to be available at a multiplexer. So because we have 16 words, those are going to be 16 inputs to that mux, and we need to select one from that 16. So this is a 16 to 1 mux, and obviously to select between 16 options, we would need a 4-bit sequence that is essentially provided by the block offset over here. So that's a 4-bit select essentially. So that's how we get the 32-bit data, and this is a wider cache. That's how we are able to do it. Okay, just to give you guys some context here, the cache used for an embedded processor called Intrinsity Fast Math. It uses a MIPS architecture and a simple cache implementation. It has two 16 kilobytes caches, separate for data and instructions, so that you have a faster overall cache. So this is an example of that particular embedded processor. Alright, now let's take a look at how read and write are different. We have seen this particular table before, but now it's going to add some more detail to it. So read and write. Read, you could have a hit or a miss. Write, again, you could have a hit or a miss. So when you're trying to read things from the cache, if you have a hit, that means that the processor simply reads that particular data from cache. And if you miss it, then you try to fetch an entire block, which could be a collection of words, from DRAM into the cache, and then read the cache. Note over here, because you're bringing the entire block to leverage spatial locality, you may be able to leverage that, or if the block is too large, then you might not take full advantage of that. And we'll see later on in graphs where this is a problem. This could be a problem. Next, write hit. If it's a hit, that means that the cache and memory are mapped correctly. Then we simply write to cache and update the entire block of that DRAM. When we miss that write operation, then we fetch an entire block into the cache. So from memory to cache, write that word, so change that word in cache, and then we update the memory. So when you do that, in that moment, the cache and memory will be holding the same block, so that you can check for consistencies. Alright, let's move on and take a look at what is the best block size. So we've taken a look at an example where we had 1 word per block, and then the next one we saw 16 words per block. But what would be a general conclusion? In this table above, we have 2 different programs. One is a C compiler, one is a circuit simulation software, SPICE. And for each program, we are considering a cache block size of 1 word per block, 4 words per block, and the same for SPICE. And if we start with this, over here we have the miss rate for instruction and data laid out in these 2 columns, and a combined miss rate in the last column. As you can see, if you increase the block size from 1 to 4, you are going to have a lesser miss rate because you have 4 more options to choose from. So a larger selection will have a lower miss rate. That's pretty straightforward to see. That same thing is clear when you see the SPICE. So when you go from 1 to 4 words per block, the instruction miss rate goes down, data rate goes down, and also the combined miss rate goes down. So that's the benefit of having more words per block. But what is the limit? Does it keep going down? Can you indefinitely improve the miss rates or make them smaller? The answer is no. As you can see over here, these particular lines correspond to a different cache size. So these are cache sizes. And obviously, if you have a small cache, you are going to have a higher miss rate than when you have a really big cache. So that's going to be the trend as far as the cache size goes. But inside, say, if we assume that we are working with a 1 kilobyte cache, we are referencing to this line plot here. If you have 4 words per block, you have this is bytes, so 4 bytes. That is going to be 1 word. Your miss rate is higher. As you increase the block size, it goes lower. So when it goes lower, we are essentially leveraging spatial locality very well to lower this miss rate. But if you go even further, the gain of spatial locality decreases as the block size increases, since you're getting further and further away from the local location. Not just that, if the block size is too large, the number of blocks stored in the cache is going to be too small, which means that there is going to be greater competition for these blocks. And a block will be bumped out of the cache before many of its words are accessed. So we are going to have to choose the appropriate block size so that we get the best miss rates or the least miss rates. On a more serious note, a bigger problem than miss rate is that larger block size means a longer time to swap blocks when there is a miss, or when we are writing, it could be longer time to write blocks even in a case of a hit. Now we are going to look at improving the cache performance in the next lecture.